Every single night, your brain puts on a show you didn't ask for. You close your eyes, lose consciousness, and somewhere between sleep and waking, you're running through a building that doesn't exist, talking to someone who died years ago, or flying over a city that looks familiar, but isn't quite right. Then your alarm goes off and most of it vanishes. You're left with fragments, maybe a feeling, maybe nothing at all. And the question that's been sitting at the center of neuroscience and psychology for over a century is embarrassingly simple. Why does this happen at all? It turns out there's no single clean answer. Dreams have been studied from almost every angle, and the more researchers dig into them, the stranger the picture gets. What we do know is that dreaming isn't random noise. It's not your brain malfunctioning while it powers down for the night. Something is genuinely happening in there, and it appears to matter in ways that we're only beginning to understand. Let's start with the basics. When you sleep, your brain doesn't go quiet. It cycles through several stages, and the one most associated with dreaming is called REM sleep, which stands for rapid eye movement. During REM, your eyes dart around behind closed lids, your brain activity spikes to levels close to waking, and your body becomes temporarily paralyzed from the neck down. That last part is actually intentional. Your brainstem sends out signals that effectively switch off the motor neurons in your limbs so you don't physically act out what's happening in your dream. People with a condition called REM sleep behavior disorder lose that paralysis, and they do act it out. They kick, punch, and shout. Some injure themselves or their partners without ever waking up. It's one of the clearest pieces of evidence that what's happening during REM isn't passive at all. This selective muscle paralysis during REM is so complete that even basic physical responses are inhibited. Your eyes can move, your diaphragm can work to keep you breathing, and your heart continues beating, but voluntary movement is essentially frozen. The paralysis affects the major muscle groups throughout your body while leaving the autonomic nervous system untouched. This creates an interesting paradox. Your mind is intensely active while your body is locked down, creating a kind of conscious isolation that might be essential to the dreaming process itself. If you could move freely while dreaming, the real world would become dangerously confused with the dream world. Your first REM period of the night only lasts a few minutes, but as the night goes on, REM cycles get longer. By the time you're approaching your final hours of sleep, REM periods can stretch past 45 minutes. Which means the most vivid, most narratively complex dreaming tends to happen right before you wake up, which is also why morning dreams are the ones you're most likely to remember. Cut your sleep short by an hour, and you're disproportionately cutting into the part that contains the most dreaming. So what is the brain actually doing during all of this? One of the oldest theories, and still one of the most debated, is that dreams are a byproduct of memory consolidation. The idea is that during sleep, your brain replays and sorts through experiences from the day, deciding what to keep and what to discard. Dreaming might be the side effect of that process, a kind of mental static generated while the filing system runs in the background. Research from Mackie Walker's lab at UC Berkeley showed that students who slept after learning new material retained significantly more than those who stayed awake. And during sleep, the hippocampus, which handles short-term memory storage, actively communicates with the cortex, transferring information into longer-term storage. Whether the dream itself is part of that process or just a consequence of it is still being worked out. The memory consolidation process appears to involve multiple stages of refinement. The brain doesn't simply copy information wholesale from short-term to long-term storage. Instead, it extracts relevant details, discards irrelevant information, and integrates new memories with existing knowledge structures. This process requires significant computational work, and dreaming may represent the brain's way of running these consolidation routines at full capacity. Some researchers believe the bizarre, fragmented quality of dreams actually reflects the brain's attempt to isolate and process specific memories without interference from normal sensory input. There's a competing theory that takes dreaming much more seriously as its own thing. It's called the threat simulation theory, and it was developed by a Finnish neuroscientist named Antti Raivansuo. His argument is that dreaming evolved specifically to give animals a safe space to rehearse dangerous situations. Think about how many dreams involve something threatening. You're being chased, you're late and unprepared, you're falling. Something is wrong and you can't fix it. Raivansuo's point is that this isn't a coincidence. He argues that the content of dreams is heavily biased toward threatening scenarios, because those are exactly the situations where mental rehearsal would provide a survival advantage. An animal that has already simulated being hunted in some sense has practiced its response. The brain doesn't know the threat isn't real. What makes that theory interesting is how it holds up across species. Rats dream too. And we know this because of a famous series of experiments run by Matthew Wilson at MIT. Wilson's team implanted electrodes in the hippocampus of rats while they ran mazes during the day. They recorded the specific firing patterns of neurons associated with particular locations in the maze. Then they watched those same rats sleep. During REM, the same firing patterns appeared again in the same sequence, as if the rats were mentally running the maze a second time. Some patterns play back at roughly real-time speed. Others replayed faster, like a brain running a highlight reel. The rats weren't just sleeping, they were doing something with what they'd experienced. Birds show similar patterns. Zebra finches learn their songs during the day, and during sleep, the same neural sequences that fire when they sing play back in the song control regions of their brains. They're rehearsing. Whatever function dreaming serves, it clearly didn't start with humans, and it didn't start recently. This goes back a long way in evolutionary history, which suggests it's solving a problem that mattered enough to stick around. The widespread nature of dreaming across the animal kingdom suggests it's solving a fundamental problem that transcends species. Primates, carnivores, and even some marine mammals show evidence of REM sleep and likely dreaming. The fact that such metabolically expensive processes, REM sleep requires significant energy and seems to offer no obvious waking advantages, persist across so many species indicates that the cost-benefit calculation must favor survival. An animal that doesn't dream appears to be at a disadvantage in ways that are still being uncovered, though whether that disadvantage is cognitive, emotional, or something else entirely remains unclear. Now, here's where it gets stranger. Sigmund Freud famously argued that dreams are the disguised fulfillment of repressed wishes, that the bizarre imagery and fractured logic of dreams are the unconscious mind expressing things the waking mind won't allow. Most neuroscientists today don't put much stock in that specific framework. But there's a modern version of a related idea that has more support. It's called the emotional processing hypothesis. And the core claim is that REM sleep helps the brain process emotionally charged experiences by replaying them in a neurochemical environment that's calmer than waking life. The key detail is that during REM sleep, levels of norepinephrine, the brain chemical closely tied to stress, drop significantly. Robert Stickgold at Harvard and Matthew Walker have both pointed to this as potentially important. The idea is that the brain revisits difficult memories during REM in a state that's stripped of the stress response, which might help take the emotional edge off them. People who get more REM sleep after a traumatic event show lower levels of distress when recalling it later. People with PTSD, who often have disrupted REM, tend to replay traumatic memories with the full emotional weight intact. There's even early evidence suggesting that certain PTSD treatments work partly by improving REM quality, allowing the brain to finally do what it couldn't do before. Dreams also appear to play some role in creative problem solving, though this is harder to pin down. The classic story is Auguste Kekule, a 19th century chemist who reportedly dreamed of a snake eating its own tail, and woke up with the insight that benzene molecules form a ring structure. Whether that story is fully accurate is debatable, but there's a genuine body of research suggesting that the loose, associative thinking that characterizes dreaming can help the brain find connections between things it wouldn't link during focused waking thought. REM sleep makes the brain more likely to notice distant, indirect relationships between concepts. That kind of thinking is exactly what you need when a problem doesn't have an obvious solution. One experiment by Ulrich Wagner and colleagues at the University of Lübeck gave participants a tedious math task that had a hidden shortcut they weren't told about. Participants who slept between two testing sessions were nearly 3 times more likely to discover the shortcut than those who stayed awake. They weren't consciously working on the problem during sleep, but something during sleep was reorganizing the information in a way that made the answer easier to see. The same pattern holds for other types of cognitive challenges. Musicians who practice a new piece before sleeping master it more effectively than those who practice and then stay awake. Language learners who sleep after studying vocabulary retain more words and access them faster. This isn't simply about memory storage in the traditional sense. It's about the brain reformatting information, finding optimal pathways to solutions, and reorganizing complex knowledge in ways that become apparent only after sleep. The sleeping brain seems to be running a completely different kind of computation than the waking brain, one optimized for insight rather than focused attention. There's also a theory on the more radical end of the spectrum called the activated synthesis model, proposed by psychiatrist J. Allen Hobson back in the 1970s. His argument was that dreams aren't meaningful at all. During REM, the brainstem fires random electrical signals upward into the cortex, and the cortex, being a narrative building machine, tries to construct a story out of the noise. The dream, on this view, is your brain doing the best it can with random input, which would explain why dreams are so often illogical, fragmented, and full of impossible transitions. The meaning you think you find in them is something you're imposing afterward, not something that was put there. Hobson later revised his position somewhat. He acknowledged that even if the inputs are random, the cortex isn't blank. It constructs dreams out of the material available to it, meaning your memories, your fears, your preoccupations. So the content isn't entirely random, even if the triggering signal is. That's a subtle distinction, but it matters. It's the difference between your brain generating nonsense and your brain generating a strange, personalized, emotionally relevant kind of nonsense that may still tell you something. What we don't have yet is a single unified explanation. The memory consolidation account, the threat simulation account, the emotional processing account, and the activation synthesis account are all drawing on real evidence. They're probably not mutually exclusive. REM sleep may be doing several things at once, and dreaming may be partly a consequence and partly a contributor to each of them. The brain is not the kind of organ that runs one process at a time. What does seem clear is that dreaming is not optional, at least not for long. People who are selectively deprived of REM sleep, woken up every time they enter that stage, show significant deterioration in mood, concentration, and emotional regulation within just a few days. When they're finally allowed to sleep normally, the brain rebounds hard into REM, spending far more time there than usual, as if trying to make up the deficit. That rebound effect suggests REM sleep isn't something the brain is willing to skip. Whatever it's doing in there, it considers it necessary. The average person spends roughly 2 hours dreaming every night. Over a lifetime, that adds up to something close to 6 full years spent inside experiences the waking world can't touch. Most of it disappears before breakfast. Some of it sticks around long enough to feel significant, though the significance is usually hard to describe. The content ranges from utterly mundane to deeply bizarre, and the line between the two can shift inside a single dream without any warning. Researchers can now tell with reasonable accuracy when someone is dreaming using brain scans, but they still can't read the dream itself. The content, the imagery, the feeling of it, all of that remains locked inside the experience of the person having it. Some labs are making early progress using machine learning to decode rough visual patterns from brain activity, matching neural data to categories of images people reported seeing. It's far from reliable, and it only captures the crudest outlines of the visual content. The narrative, the emotion, the inexplicable logic of why you were suddenly in your childhood home talking to a stranger who you somehow knew was your coworker, that part remains completely out of reach.